Hello everyone, my name is Kaiyue, a PhD student from the Australian National University. Today I'm happy to share with you my research work on depth completion at this workshop. From a broad view, my research in this work is about image quality enhancement. It aims to improve the visual quality of the input image in order to better identify key features and make them more suitable for a specific vision task. It typically includes four primary tasks. Image smoothing retains main structures and removes insignificant textures in the image. Image completion fills in missing values or damaged regions and recovers continuous structures based on available pixel values. Image super resolution restores the high-resolution image from the low-resolution input. Contrast enhancement increases the contrast of the image content for clearer visualization. In this work, we present a subtask of image completion. It's called depth completion, which aims to recover dense depth from the sparse depth image. The specific task we are focusing on is unsupervised depth completion. It means the model is trained without using any dense depth ground truth or other manual annotations. Compared with supervised models, they can largely reduce expensive human labeling work. In this framework, the input itself is used as a supervision signal to enforce depth consistency. However, only use the sparse depth as a supervision signal. The structure degradation becomes more severe when lacking of dense ground truth. It basically refers to the poor localization or recovery of object structures. To deal with the structure degradation issue, existing unsupervised works take the RGB image as an additional input at both training and test time. They basically assume that the RGB image can provide clearer and more dense structure information. They also use the second image, either from stereo or adjacent video frames, for implicit supervision during training. We say the supervision is implicit because the loss does not directly penalize depth, but the results derived from it, that is, the warped image. However, these models are highly dependent on images and become less practical and implementable in real-world applications. Our model only takes sparse depth as input and is formulated as an autoencoder. To reduce structure degradation, we propose to use the image to guide latent features during training. At test time, no image is required. Our model is more practical and largely benefits the scientific body of literature in the unsupervised depth completion community. This is our network architecture. It's composed of four primary parts. The encoder extracts features from the input and transforms it into latent features. The latent feature guidance penalizes the difference between latent features and the image. The decoder recovers dense depth from latent features. And the training loss consists of image supervision loss and the image guidance loss. To validate the effectiveness of the proposed intermediate image guidance, we compare the performance with and without this image guidance. We call the model without the image guidance as the vanilla model. As shown in this figure, we clearly see that vanilla latent features are sparse and cannot reflect any structures or shapes of the car. The dense depths recovered from it present severe artifacts, especially around the car boundary. By contrast, our image-guided latent features can properly reflect the car structure, and the output depth is more accurate visually around the boundary. Note that on the kitty validation set, our RMSE surpasses the vanilla autoencoder by more than 40%. This huge improvement further indicates the effectiveness of our proposed intermediate image guidance. Here is the quantitative evaluation. Our model significantly outperforms the state-of-the-art model IR with much fewer parameters. It shows the superiority of our model in the depth-only setting. We also achieve comparable performance to the state-of-the-art methods with RGB input. It's very natural that they outperform ours in numbers due to the extra RGB input and additional information used during training. Here is a visual comparison. Our model has better performance in some important but challenging regions, such as the car boundary, trees, and poles. This can be also reflected by area maps, where bright colors correspond to larger areas. Here is a visual comparison with other two state-of-the-art methods with RGB input. Our model can still achieve comparable performance even without the image as input. To conclude, in this paper, we have proposed an unsupervised model for depth completion. It only takes sparse depth as input without the image as an extra input. Also, in training, it doesn't need a second image for implicit supervision. At test time, no image is required. Hence, our model is more practical and implementable in real-world applications than those need images in both training and testing. We have achieved comparable performance to state-of-the-art methods. In our future work, we will use other cues for intermediate guidance, such as point clouds, boundary information, and semantic labels. We also plan to apply the proposed unsupervised framework to other computer vision tasks. As references used in this presentation, and you can have further reading if you are interested. Thank you very much for your listening, and I'm looking forward to further communicating with you and receiving feedback from you. Thank you.